I mean, the reason we posted some of the lectures and I worked over the break to finish them up has to do with the fact that you will need to start working on the homeworks before the lectures. Otherwise, you will not be able to do anything. Okay? Now, that may be tough for some, all right? But you're all adults, and you should learn how to deal with it, right? And the notes are really self-explanatory. I think you don't really need me to give you the lectures. You can read the things and manage to do the homework. So obviously, I think there are like 3 sets of lectures that they are missing, which means that even if we teach 3 lectures a week, there's absolutely no way to cover those topics. Okay, that's one thing. And to make it a little bit worse, I'm not here next week. Okay, so that answer your question? Sort of. All right. All right. I want to be sure that we have all the questions answered. Okay. So I'm going to try to spend basically 2 lectures on discussing about unsupervised learning and model reduction, and all of this goes with the type basically continuous latent variable models. I mean, up to now, basically the latent variables that we have seen are discrete variables. So now we will try to see how we can move on to continuous models. All right, so my pointer is misbehaving here. All right. So let me discuss the problem of interest. Suppose that you take a hand-written digit, the number 3 here. All right. I mean, if I go around and I ask each of you to write down the number 3, you're going to give me completely different versions of this, depending on your the way you write, depending what pen you use, depending on how you feel today. But they're all 3, all right? So even though this picture, if you digitize it in 100 by 100 pixels, it looks very high dimensional. If I give you lots of these different 3s, they are really living in a very low dimensional space, okay? And in this particular case, if I take these images and I rotate them, I translate them, the space they live are, it's literally 3-dimensional. You can think of 1 rotation and 2 translations, X and Y. So the question is, when you do model reduction, you try to identify to what space literally these digits 3 are embedded. Can you figure out that it's not really 100,000, it's 10,000 dimension, but it's actually 3? And how can we do that? So that's what we will discuss today. I know you have seen these things in other courses, so I'm going to try to give you only the very essential information. Now, why is this going backwards? All right. Okay. So. So in this particular problem, the latent variables that have to do with identifying that all of these numbers are 3 are really the 2 translations and rotation. So when I give you this 3, all right, I have not telling you how much I took this image and I translate it and rotate it to take the location that you see there, okay? So the latent variables here are basically the translation and rotation parameters, and that's what we will try to identify. Now, in the context of digits, you can have many other latent variables. So, for example, you can think this image, you take it and you deform it, all right? You distort it. So you can actually talk about nonlinear sort of ways of manipulating this image. But you don't really need these nonlinear manipulations to get a nonlinear manifold, because even if you take this image and you translate it in X or Y directions, the manifold that you get is really nonlinear. I mean, you can think of this image, right? If you take a pixel here that is white and you move this to the right, suddenly this will become blue, and then if you move it a little bit, it will become again white. So this manifold that we're trying to recognize is nonlinear. Okay. I keep going backwards on this thing. All right, so what I'm going to do is I'm going to try to give you the more advanced outlook of these continuous models, and then I'm going to go to simplistic models. So I'm going to start at something that looks a little bit more difficult, okay, not really very complicated, and then we will revisit this topic on Thursday as well. So what I would like to do is I would like to follow what's called a generative point of view of model reduction here. So not only we want to find a latent representation of some high-dimensional data, but also we would like to be able to generate more data than the ones that I gave you. Okay? So somehow, if the data come from some distribution P of x, we would like to use this as a mechanism to sample from P of x. So in the previous case, if I give you, let's say, 1,000 digits 3, what I would like you is to have a model that can produce as many other 3s as you like that are coming from the same distribution, okay? So that's a generative view of this unsupervised learning problem. So what we will do is we will define Z to be the latent representation of this high-dimensional data X that we started with, and we're going to put some prior model P of Z on Z, okay? Then we're going to generate a mapping from low dimensions to high dimensions. And so we're going to postulate some model from P of x given Z. Now you can appreciate that if you have P of Z and P of x of Z, you can produce P of x from these two, but also you can produce the reverse mapping, which is P of Z given x. So P of Z given x is the traditional way of thinking of model reduction, right? Give me your data x, I'm going to give you some low parameterization of x, but here we emphasize the generative aspect. Give me Z, and I can actually tell you what the corresponding x is. So this sounds a little bit different from what maybe you expect of model reduction. So, so let me postulate some parameterizations for these two distributions. So let's say that we put P of Z to be a standard a multivariate Gaussian, mean 0, covariance I. And let's make this generative model from Z to X to have a mean that is W times Z plus mu. And in this case, I'm taking an isotropic covariance, sigma square I. So can you look at the mean and tell me what W you expect to be if this is sort of a model that is going to try to do model reduction? So if, let's say, the dimensionality of X is RD, what do you expect the dimensionality of W to be? I mean, obviously, Z has to be some low dimensional representation, right? So it has to be some vector in Rm, where M is much less than X. Which is RD. So what's the dimensionality of W here? If X is in RD and Z is in Rm, what is W? In D by M, correct? Okay, so effectively, there is a lot of parameters in this model. We have somehow to be able to identify what W is, what mu is, what sigma square is, and we will see different techniques of doing that. So if you actually take this particular model, it will lead to what is called a probabilistic principal component analysis, and we will see more details of this on Thursday. But effectively, literally, these two equations are defining the whole model, okay? A prior model on Z and a generative model that takes me basically from a latent representation Z to the high dimensional space of X. So there are different versions of this model. So let me throw you the names because you will see special sections in the notes. When you write this generative model, you can actually generalize the prior on Z, and you can put any mean you want and any covariance metrics you want. As you will see in the notes, you don't add anything new to the model, right? So if you try to generalize, you can actually write this model to take exactly the same model as the simple case that you see here. So you can change the definitions of W, mu, and sigma squared there, and somehow you can take a general model with this, a general model with this mean and covariance and simplify it. What is interesting here is what in the generative model, what is psi? If psi is a general diagonal matrix, you get what is called a factor analysis. If psi is basically sigma squared I, then you get principal component analysis. So if psi is in general, a diagonal matrix, factor analysis. Now we will not allow psi to be a full matrix, because if psi is a full matrix, you don't achieve any model reduction with this, right? I mean, if the whole idea here is, right, to get something that is way more efficient than a multivariate Gaussian. So if you take this psi and you make a full matrix, there is really nothing that you have gained, okay? So that will not be happening. So let's see a graphical representation. This is a very important picture if we can understand it here. So let's take that Z is one-dimensional. So this is a prior model P of Z. So imagine that somehow your data are in 2 dimensions and you project them in 1 dimension, but we're going to do it in a generative way. So we take P of Z to be a Gaussian. You sample from this distribution P of Z, that's a Z hat, okay? And then you're going to use the generative model and try to map the Z hat to some X, all right? And you see that X here is a Gaussian distribution. So effectively, what you need to do is, so this is scalar, so you basically need to move this by some scaling coefficient W plus some distance mu. It will bring it to this point, and then you have to put a Gaussian around it with a variance sigma squared. Okay? So effectively, for any sample in Z, you can generate data in high dimensions. Now, the traditional way of looking at model reduction would be to do the opposite, to say, give me a point in x1 and x2 space, and tell me what is the reduced representation. The way that I would like you to see is the other way around. Right? Give me a point in low dimensions, and I will tell you what is the generated x, the corresponding x, in 2 dimensions in this case. Now, if you take this prior Gaussian that we have for Z, and you take this generative model and you integrate Z out, then effectively what you get is a distribution for x that looks like this. All right, so it has a mean mu, okay, and where is my, you can see actually the equation here, all right, so this is the most general case. So I have a prior that is very general. I have my linear term here in the mean is W times Z plus mu, and you can see when you integrate Z out, you get W times mu 0 plus mu, and then psi, all right, plus W sigma 0 W transpose. So the key idea here is when you integrate Z out, the distribution that you get is a multivariate Gaussian. So the only way that anything we discuss can stand as a model reduction scheme is if the number of parameters to describe this multivariate Gaussian, if the parameters that you need to describe W and mu 0 and psi is less than the number of parameters that you need to describe a very general multivariate Gaussian. I mean, we do the whole thing, right, to get a Gaussian. So obviously we need to be sure that by introducing this structure, this generative model, the number of parameters that we would need here has to be less than the ones that we need to describe a multivariate Gaussian. And for a multivariate Gaussian, how many parameters do we need in D dimensions? What's the order of the parameters that we need in D dimensions? If I give you, P of x, x in D dimensions, what is the number of parameters that you need? How many parameters for the mean? D, and for the covariance? D squared. So we would need to do way better than D squared. If we don't, there is nothing that's really achieved with this sort of a model. Okay, so somewhere we're going to have to do a count of the number of parameters that's involved in the model. All right, so I am going to try not to, the slides are really, have lots of details, very easy to read, right? So I'm going to try only to highlight some of the elements. So the first thing is, I mentioned that if you try to use a very general prior for the z's, you are not really adding any complexity to the model, right? So effectively, taking that mu0 is equal to 0 and sigma 0 equal to I is really the general case, because every other case can be actually written in the same form for the distribution P of x. So if I redefine basically the parameters, right, I can get the same results as I get in the case of mu0 equal to 0 and sigma 0 equal to I. You can appreciate this because, for example, if you can see, come on. For example, if you look here, right, you have W sigma 0 W transpose. If you want to get rid of sigma 0 and get W W transpose, you can define a new W that looks as W sigma 0 to the power of 1/2. All right? Similarly, you can incorporate the W times mu0 inside mu, okay? So you're not gaining anything by having a non-zero mu0. So how many parameters do we need for this model? Can somebody count them? So we mentioned that you told me we need D squared for a full multivariate Gaussian in D dimensions. Do we have a D squared count here? I mean, look at all the variables that have been introduced. How many, let's say we use a very general diagonal psi. How many variables are those? D. How many W's do we have? How many W's? What's the dimensionality of W? Is D times what? D times M, all right? And if M is significantly less than D, because we're talking about dimensionality reduction, that's less than D squared, right? And that's exactly what we're interested to do in this problem. So we're basically going to an order of MD parameters versus D squared, okay? And that's the objective. Now, if you really want to see this problem in the traditional way of model reduction, you can use Bayes' rule and ask yourself, if you give me a point x in high dimensions, what is the corresponding basically distribution in latent space? And it's nothing but an application of Bayes' rule for linear Gaussian models. So if you multiply the previous model, we had the probability of x given z times the P of z, you normalize it, you get a distribution for z that looks like that. So this is the mean. All right, this is the mean. This is the covariance. You notice the covariance here does not depend on the point I, all right? So there's no I here. But the mean basically depends, it refers to every particular point. So for every xi, there is one zi, the same way we have seen this with latent variables before. So if you're interested in a sort of engineering perspective here, if somebody gives you an x and it tells you, can you do some dimensionality reduction of these x's, then what you can do is you can report basically the mean of this distribution and say, you know what, this point x is going to go to this value mu, but keep in mind there is some error bars around it defined by this covariance matrix. So this mean of the distribution of z given x is called the latent scores or latent factors in practice. So let me do one example. This is from Murphy's book, but before even Murphy's book came about, I participated in a PhD exam in somewhere in Germany, and the student basically had nothing to do but do model reduction of lots of data from different manufacturers of cars in Germany. So what we have here is we have a case of data that they live in 11 dimensions. We have 387 data points corresponding to different types of cars. And we want to do model reduction of this high dimension data. We want to project them in 2 dimensions. So the plot that I'm going to show you takes this data, it projects them from 11 dimensions to 2. And in addition, what it does is it projects the unit vectors in the 11-dimensional space. So it projects these vectors 1, 0, 0, 0, 1, 0, 0, etc. in 2 dimensions as well. So what you get in this case, all right, you get, you know, these are the projected points from the different data. And by accident, it comes that the horizontal axis corresponds to the input dimensionality that is related with the dealer and the retail price of the car, and the vertical axis comes to be related with the fuel efficiency of the car. This is sort of misleading here because there's absolutely no reason when you do this latent representation that this will have any physical meaning. So in this case, obviously, they were trying to put some physical meaning, and it just came, and it's like, oh, you know what? When I project the axis corresponding to the retail price, that comes to be the horizontal axis in the 2-dimensional space. It was an accident, okay? But this is how it all came about. But keep in mind that generally speaking, there is, you know, there's no physical meaning that you can assign to these 2-dimensional representations. Okay, we have an issue with the things I discussed in a very abstract way, and the issue is that we have to compute different parameters like W, but unfortunately these parameters don't seem to be unique. So let's see why there is a non-uniqueness issue here. So remember that if you integrate this out, the distribution of x that you get, for the general case of a factor analysis, you had some mean psi plus W transpose. Notice, so we're going to have to compute psi, we're going to have to compute mu, and we're going to have to compute W. But notice there is an issue of non-uniqueness of W here, because if W changes by a rotation R, then this W curly W transpose comes to be equal to W transpose. So effectively, you can insert any rotation, and it will not affect basically the covariance matrix that you get here. So if you're trying to do, let's say, maximum likelihood estimation, and we will do that, you're going to have a problem, because when you solve the optimization problem, you will not be able to be unique in the context of identifying this rotation. So we will have to do something about this problem. Now it says here, if we want to get rid basically this non-uniqueness in the context of the rotation, it says we need to remove m times m minus 1 over 2 degrees of freedom, because that's the number of orthogonal, that's the number of the R rotations of size m by m. Can you tell me from where is this coming from? Why the number of different rotation metrics that you can have is m times m minus 1 over 2? The upper triangular. So remember this rotation, right? It's an orthogonal metric, so you can think of all the columns being orthogonal to each other. So how many unknowns, if you look at the typical R matrix and you start from column 1, how many unknowns you're going to have in column 1 of the matrix R in m dimensions for an m by m matrix? If you look at column 1, how many parameters do you need to describe it? Well, I'm going to say m minus 1. Why m minus 1? Because, you know, we are going to make this all the columns orthonormal, so the magnitude equal to 1. right? So there is a constraint. So column 1 is going to have m minus 1 unknowns. How about column 2? Remember, we're going to have the same constraint as column 1, but the difference is also is going to be orthogonal to the first column. So how many unknowns? M minus 2. So keep doing this and add them up. You get m times m minus 1 over 2. All right? So somehow, we're going to have to remove these degrees of freedom that correspond to the number of possible rotations for matrices m by m. So effectively, for the general case of using a factor analysis, we're going to have d numbers to describe this psi, okay? We're going to have m times d to describe w, but then we're going to have to subtract this unidentifiable degrees of freedom for rotations. So we get that basically the number of parameters that really we can estimate uniquely is d plus md minus m times m minus 1 over 2. And here is the tricky part. If you really want to have model reduction, this has to be better, less, or equal to d times d plus 1 over 2. What is that? You remember, to get model reduction, the number of unknowns that you get has to be less than the number of unknowns to describe a multivariate Gaussian. So if you forget the mean and you look at the covariance of a multivariate Gaussian, what is d times d plus 1 over 2? You remember the covariance matrix is symmetric, so what is d times d plus 1 over 2? Is the degrees of freedom, right, to define a symmetric matrix in d by d. So if you take this and you set it equal to that, you basically get an upper bound to the model reduction that you can achieve with this type of factor analysis. So you cannot really go to anything m that is higher than this value. And a recommendation here is, don't ever go and compute this number and you do model reduction in these dimensions, because in more typical settings, this will overfit, okay? But theoretically, at least you know that there is a maximum m that these models make any sense. All right. Are there any ways to actually resolve these issues of non-uniqueness of the parameters for these models? The answer is yes. And depending on what you do, you get a different method with different names. So a possibility would be to make the W matrix orthonormal, and we will get the principal component analysis on that. Another possibility is to get W to be lower triangular. You can actually introduce some priors that induce sparsity in the weights. And so ideas from lasso and automatic relevance determination, and I will do this type of topics in the next few lectures, can be used basically to reduce the number of unknown parameters. Another possibility is, you know what, to say, you know what, I am going to fix what R is, right? You fix what R is, and that resolves the issues. And a little bit more sophisticated, that actually gets rid of this problem, is to use a non-Gaussian prior for P of Z. And that leads to another method, and you have a homework on this, that is called independent component analysis. Okay? So there's something that if somehow you can get rid of this Gaussian nature of P of Z, that can resolve in part some of these problems, and this has lots of applications, as we will see on Thursday, I believe. Okay. So as I told you, I'm trying to give you the big picture without the actual derivations yet, right? And in the big picture, you may say, okay, these models are Gaussian. Do I expect really my data to be Gaussian, you know, and do generative modeling and dimensionality reduction with Gaussian models? The answer is no, in general. But you know what? You can use a mixture of factor analyzers. And I want you to concentrate on these three equations on the bottom. And actually, most data, even complicated data, can be modeled quite nicely with these three equations. So I want you to look at this and tell me what have I changed to my model to get this mixture of factor analyzers. So it can be a mixture of PCA models, of probabilistic PCA, of anything. Tell me what is new here in these three equations. I mean, immediately I can see that in the conditional distribution P of x given z, I put an index q equal to k. So what is the variable q, which a discrete variable doing in this case? So obviously I'm going to use a mixture of these models, and q equal to k tells me use the k mixture. And for the k mixture, I'm going to have parameters mu w that have an index k, and in this case, to make simplifications, I'm using the same psi. Okay, so all the factor analyzers basically have the same psi, but the mean, come on, but the mean and w have an index k. Okay, so what you need is, you need basically a probability model to select which model you're using, and obviously that's going to be a categorical distribution defined with probability pi. Okay, and so let me show you a nice example of this. So suppose that I give you all of this weird data, and I tell you fit them on a straight line, right? Do some projection on a straight line. You're going to say, I cannot fit these things in one dimension, right? They don't belong in one dimension. But you know what? If you take a mixture of 10 linear projections, you can actually do local fitting, as you can see, okay? And this is, something you can visualize that makes sense. But in reality, these mixture models are fitting very well, even very high dimensional data. So this should be something you should consider when you have to deal with this type of problems. And the number of parameters, by the way, are reduced. They're the same as before. Before we had, for one model, we had these square parameters, and we reduce it to m times d. For k models, we are going to reduce it from k d squared to k times m times d. And I know you have not, unless you have taken a course on these graphical models, you may not appreciate this graph, but basically, conceptually, the whole model looks the way that you see here. So to define x, right, you have to condition it on the type of model that use q and the latent variables z. And each model has its own parameters, psi, mu k, and wk. And we have k of those models. We have n data x, okay? And to define the distribution of q, we need this parameter pi. So this is a nice graphical representation of a mixture model. And it's literally these three equations. All right? I think you have a homework problem actually also on this. And I think if you do this, if you write a model for probabilistic PCA, and we will discuss what that entails, this is basically 5 lines of program. And together with this, really in like 10 lines, you can have the whole thing implemented, and you can do interesting things such as what you see on this plot. All right. Now, so this is sort of as an introduction, right? And you may ask, why are we going to do a probabilistic version of this? Or are we going to do a Bayesian version of this? And the answer is all of the above. The nice thing is if we do a probabilistic formulation of these latent variable models, actually we will figure out that we can bring things that we already know, such as expectation maximization, to compute these parameters. We can actually do a fully Bayesian model, all right? And you can do fancy things, such as, when you do model reduction, and you go from d dimensions to m dimensions, how do you select m? Right? That requires sort of a comparison of models, and the only way to do this is in a Bayesian setting. Okay? You cannot do this in any deterministic way. I mean, there are heuristics that we will see, but really you need the model comparison based on some Bayesian criteria. Okay, so now we are going to go slowly backwards to see the history of these models. But effectively, I'm going to be repeating with a lot of details the things we already have seen. So principal component analysis comes with different names depending what books you read, from what community you're coming. And so in principle, it's the same thing as Carhonen-Loewe expansion, is the same thing as proper orthogonal decomposition, and you guys can think of many other names that escape me, but they're all sort of, equivalent. The reason that people use PCA can vary again with the communities. So lots of people use PCA simply to do visualization of data. So if you have very high dimensional data, they say, if I project them in 2 dimensions, like the car problem, I can do visualization. But really for us, the whole thing is to do dimensionality reduction or compression of the data, of high dimensional data. So I'm going to give you 2 formalisms from where historically PCA came. And one of these formalisms, it says, find a projection of the data in a subspace, of a low-dimensional subspace, that maximizes the variance of the projected points. So you can see this in 1 dimension. These are projected points on this line, right? If we do the projection here, we want these points to have maximal variance. So that's formulation 1. And the second formulation says, you know what? Find this subspace, let's say here U1, so that the sum of squares of the projection errors is minimized. So basically the square of this length and the square of that and the square of that and the square of that is minimized. And it comes out that the 2 formulations, even though they come from 2 different eras, they effectively give you the same exact answer. So we need to revisit, because we're going sort of to learn a little bit on how PCA works. All right, problem definition. So let's say that I give you n data, xn from n equal 1 to capital N. The data have dimensionality d. We want basically to project the data in a space that has dimensionality less than d. All right? Effectively, what that means, right, is I want, instead of needing d parameters to define each of these data, I need to be able to define each of these x's with n parameters. That's what that means, right? With n parameters. And we assume here that m is fixed. So we don't have to worry about model selection. So we define basically the principal subspace where we're going to do these projections based on these vector UIs, all right? And these are vectors in the RD space. So you can imagine if you have 3-dimensional data, right? And you project them in a plane, still the representation is in 3D. It's just that the subspace is 2-dimensional. Okay? So it's a 2-dimensional subspace embedded in 3 dimensions. So we're going to assume that the vectors UI basically in RD define this subspace where we're going to do the projections. So let's define the mean of the points. X bar is the mean of the points. And this is the sample covariance. Okay, so remember these 2 definitions, the mean and the sample covariance. All right, so we're going to start simple, and we're going to start doing projections in 1-dimensional subspace. So let me start working with U1. So we're going to project all our points in U1, and we would like that projection to maximize the variance of the projected data. Okay? So if you take xn and you project it in U1, the projected point is U1 transpose xn. Okay? The projected mean of the data is U1 transpose x bar. And the variance of the projected data, would you agree with me, is this? Right? These are the projected points. This is the projected mean, so that's the variance of the projected points. I am writing, this is scalar here, scalar square. I am writing this parenthesis times this transpose. You can move U1 outside, you can move U1 on the other side. Will you agree that this is U1 transpose S U1? Yes? You remember the definition of S there? So would you agree that this is U1 transpose S U1? So if you agree, then what the key idea of PCA is to maximize the variance of the projected points, but obviously because we want to identify U1, we're going to make it to have magnitude equal to 1. So we're going to maximize this with the constraint that this is U1 transpose U1 is equal to 1. So you have seen this problem on the top, right? If you take, these are Lagrange multipliers. If you take derivatives with respect to lambda 1, you get the magnitude of U1 equal to 1. If you take derivatives with respect to U1, what do you get? You get S times U1, and then you get lambda 1 times U1. So that's an eigenvalue problem. So the first principal component where you do the projections is actually an eigenvector of the sample covariance matrix S. Okay? So U1 is called the first principal component. Okay? So you will see now that the whole problem of PCA in the traditional way of looking at it is really solving an eigenvalue problem. And to be able to show this, we're going to need to show that the second principal component where we have to do the projection is actually the next eigenvector and eigenvalue of the sample covariance matrix S. Okay? Now, there is nothing that I told you yet that says that this lambda 1, what eigenvalue is. Is it the biggest, the smallest? There is nothing yet, okay? So we will wait to see where this thing leads us. So the proof actually is by induction, in case you remember this from your old days in high school. So if you can assume that you have done projection, let's say, in m-1 dimensions, and then you try to figure out what the mth vector to project is that maximizes the variance of the projected data. And then you can show that actually what you get is you get the eigenvector and the eigenvalue next in the sequence in the sample covariance matrix. Okay. So which eigenvalues and eigenvectors are you going to use, right? So let's clear this thing up. The total variance that you have is the summation of all the eigenvalues from the sample covariance, okay? And from each component, the contribution that you get is lambda I divided by this total variance. So obviously, every time you do the projection, you're going to start with the eigenvector that corresponds to the largest eigenvalue, and you keep moving down. So when you project basically in m-dimensional subspace, you're going to have to keep the m highest eigenvalues and the corresponding eigenvectors of the sample covariance matrix. This is the proof by induction, so I am not going to elaborate. If you already have projected in m dimensions and you want to find what the vector is to do projection in m+1 dimensions, literally what you need to do is, introduce the principal component um+1 and force this to be unit vector, and force that the um+1 is orthogonal to the previous principal components with this Lagrange multiplier. So when you do the eigenvalue, when you do the maximization problem, you compute that um+1 and lambda m+1 is the next in sequence eigenvector and eigenvalue of the sample covariance matrix. Okay, so the first fundamental basically way that PCA was introduced is project it to the first m eigenvectors of the sample covariance matrix, and effectively that maximizes the variance of the projected data. All right, that's how this PCA was introduced. Now, the other way is to minimize the projection error. So let's see exactly how we're going to do this. So we have, you remember we have, when you take the sample covariance and you do an eigenvalue expansion, you get basically d eigenvectors ui. So any vector, any data point xn can be written as a linear combination of these eigenvectors. And because they are orthonormal, the coefficients is nothing else but xn transpose ui. Okay? So for any data point xn, we can write this. Now, we want to do model reduction, right, in m dimensions. So what does that mean? We need to find a parameterization that only requires m coefficients, not d coefficients. So how are we going to do? We're going to do a projection in the first m eigenvectors ui, all right? Okay? So the projection is going to look as follows. We're going to approximate any data point xn as some linear combination of the first m ui's, all right? And you notice the coefficient here depends on each data point n. So there's a subscript there, n. And then, imagine that you project everything on this plane, all right? That's the first term. And then everything else has to be a component outside that subspace. So it will involve the ui's from n plus 1 to d. But notice here, these coefficients bi do not depend on n. They are the same for all data points n. Okay? Obviously, we don't want this to depend on n, because otherwise we will not only need the m coefficients to describe this projection, we will need more than m. So, right, so we need to have an approximation that only requires these m coefficients to describe approximately each data point xn. Okay? So, again, look at this equation. We will see it many times in the following slides. Every point is approximated using the m first ui's, and then we have a projection to that subspace where the coefficients are independent of n. So we want to actually minimize the error of the projection. So the objective is we set basically some distortion criteria, 1 over n summation of this approximation error square, where these are our data points that we started with. This is the approximation. And we want to do this optimization problem with respect to the coefficients z and I, with respect to the coefficients bi, but also we need to figure out what ui is. You may already anticipate that ui is going to come to be the eigenvectors of the covariance matrix, but there is no guarantee that ui has anything to do with eigenvectors, right? Because this approximation was developed completely independently from maximizing the variance of the projected data points, so we have no idea what ui is going to come to look like, okay? So we want to minimize, again, this error. If you take derivatives with respect to the z's and with respect to the b's, you compute immediately, all right? Okay, so if you take derivatives with respect to the z's and to the b's and you set them equal to 0, you compute that z and I, z and j, is xn transpose uj. In some sense you expect this, right? It's an orthogonal projection of zn in the direction uj, all right? So z and I comes to be xn transpose uj. And then with minimal algebra, it comes out that these coefficients b, that they are the same for all points n, they come to be the projection of the sample mean of the x's. All right? So to get bj is a projection of the sample mean in the direction uj. Okay? So you can appreciate actually what that means, right? That's why there's no dependence on n, because you're actually projecting the sample mean on uj. So let's compute the error. What is xn minus xn hat, where xn hat is that? So we, would you agree with me that xn is equal to the first summation? From where do we get this? My data point xn is the first summation. Can I do that? Is that okay? From where did this first term come from? I mean, UI spanned the RD space, right? From the completion of that basis, I can write basically any point xn as the projection of xn to each of the UIs, all right? Where I sum over all vector size, okay? Nothing new there. And then I remove the approximation. And you remember Z and I came to be xn transpose UI. And this came to be the projection of the sampled mean. And so this minus that, basically this summation is from 1 to D, this is from 1 to M. So basically combining with the last thing, what I get is a summation from M plus 1 to D. All right? So immediately you can see that the approximation error that you do, it lives in a space that's orthogonal to the subspace where you do the projections. Does this tell you anything before I show you any pixels? The fact basically that the error lives in the space spanned by the vectors from M plus 1 to D. What that tells you, what type of projections are we looking here? If you project something here and it tells you that the error is orthogonal to that space, right? This is what this equation is all about. Okay? All right. So effectively, what we have is this vector xn minus xn hat. So the error that we do lies in a space that's orthogonal to the principal subspace. I'm showing this the picture for one dimension, okay? And obviously the minimum error, right? The minimum error, xn minus x tilde, will be can be obtained by doing orthogonal projections. All right. So let's figure out what the U's are to see if they're related at all with eigenvectors. So this is what we had for xn minus xn hat, okay? This is our error function. So if we take this and we plug it inside there, right? There is a summation in n. There is a summation in the vectors ui that you see here. So if I reverse the order of summations and I put this outside and the summation in n inside, can you actually start imagining that this is equal to that? There is a summation in n and then summation from I from n plus 1 to d. If you reverse the order of these two summations, can you see why the second summation, 1 over n summation over n of this square will give me this? Can you see that? You remember we sort of highlighted this calculation before, right? You can write this as this times, this is scalar, so you can write this times the same number. You can remove one UI outside, another UI on the right, and inside what you're left is the sample covariance. All right? So effectively, what we get is, we get that the minimum of J is obtained when this is minimized. Now, without repeating any minimization problem, if you extrapolate from the previous formulation where we maximize the variance of the projected data and looking at what I have here, UI transpose as UI, can you tell me when you minimize this, what are you going to get? With the assumption that the UIs are orthonormal. what will you get? I mean, obviously, you're going to get the eigenvalue problem for S, right? So the vectors that you see here from m plus 1 to d, because you need to minimize, all right? And this will come to give you the eigenvalues of the S matrix from m plus 1 to d. Obviously, if you want to minimize, these UIs here have to correspond to the smallest eigenvalues of the sample covariance matrix from m plus 1 to d. Do you see that? I mean, if ui is an eigenvalue, what is SUI? By the definition of the eigenvalue problem. It's lambda I times ui. So ui transpose lambda I, ui gives you lambda I. So you want to minimize the sum of the eigenvalues. So which eigenvalues have to be? Have to be the smallest from m plus 1 to d. So you get basically exactly the same problem as you do when you have this formulation with maximizing the variance of the projected data on the principal subspace. So if you do, if you have, let's say, data in 2 dimensions and you project them in 1 dimension, and you know, lambda 1 is the first eigenvalue, lambda 2 is the second, the smallest. Effectively, the principal subspace will correspond to U1, all right? And this error that you do will basically be equal to lambda 2, and U2 will correspond basically to the second eigenvector. So the distortion measure comes to be this, okay? That's why when you do principal component analysis, you will see lots of people plot the sum of the disregarded eigenvalues, because that, in essence, it gives you a measure of how much error, projection error that you do, okay? So effectively, lots of people, when they try to decide what M to select, right, they say, you know what, I am going to conserve 95% of the energy. They call it energy, you know, so this has to be 5% of the total sum of the eigenvalues, and that sort of can allow you to compute in an empirical manner what M is in this sort of analysis. So conclusion, historically, 2 different formulations, none of them probabilistic, right? The maximum variance and the minimum error, and they are all sort of leading to the same algorithm, that is the principal component analysis algorithm. Okay, now how do you use this principal component analysis to actually do you know, projection in low dimensions? So if so remember the equations that we had, right? The first summation we project to the first m eigenvectors, and then there is this error that we do that's orthogonal to the principal subspace, and I give you what the answers are. So if you plug in this in there and this on for the values of b, you can write an approximation of xn by this equation that you see on the center. And you can see why there is model reduction here, right? How many parameters do you need to approximate x? Before you needed d parameters, because this lives in d dimensions, but now what actually you need is only the same coefficients. All right, so that's the whole idea. You know, this can be a 50-dimensional vector, but you only need 2 coefficients to describe it, okay? And this is how you achieve basically data compression. Now, obviously, if you select m equal to d, nothing has, you know, if you put m equal to d, actually what you get is the equation that we had seen before, where effectively the only thing involved is rather than describing, let's say, x in your original Cartesian, let's say, coordinate system, you now rotate the system to the eigenbasis ui, but still you need d of these components to describe xn. So m has to be less than d to be able to make sense out of this analysis. All right, there is if you coming from electrical engineering, right, there is a third approach to principal component analysis, and actually most probably that's the approach that you see when you take a numerical linear algebra course, and that has to do with the singular value decomposition of the covariance of the sample covariance matrix. Don't ask me, I just noticed actually before I came, this matrix, instead of S, I call it here, I think trying to conform with the notation from Murphy's book. The sample covariance matrix is denoted here as sigma hat, okay? And so try not to get confused. The slide tells you exactly what it is. So if you take the input data, so these are d-dimensional data, and you have endpoints, all right? So this is the design matrix X. So a singular value decomposition, all right, looks like X equal U, where U is an orthogonal matrix. S has the structure that you see here, I'm going to explain shortly, and V is another orthogonal matrix. And the dimensionality of these matrices is, this is N times D, all right? Let me see what we have here. This is N times, N times N, all right? N times N, N times D, and D times D, okay? And whatever is crossed out is 0, and whatever you see off diagonal on the matrix on the center here is also 0. So on this matrix S, we only have this diagonal value sigma 1 to sigma D that are basically called the singular values of the matrix X. So this is a generic decomposition that you can do for matrices that they are not squares. So I can do this for my data design matrix of N by D, and I can decompose it using two orthogonal matrices and this S matrix that has only these diagonal elements and lots of zeros. Now, why do I care about the singular value decomposition and how is it related to PCA? Here's the idea. Well, you tell me, what's the idea here? So when we do singular value decomposition, if it happens, let's say that D here is very high dimensional, right? And you want to do some approximation of this matrix of lower rank, what can you do with this decomposition? So imagine here we have a lot of zeros, right? And we have these non-zero sigmas, but let's say some of the sigmas are very small. So can you envision some sort of approximation that we can do of X, right, where something happens here? What that something is? Truncated. So basically, rather than using diagonal elements from sigma 1 to sigma D, write this expansion where we only use diagonal elements from sigma 1 to sigma M. Let me see if there is a picture. And here is the picture, right? So rather than using the full spectrum, basically, of the singular values, we use only from sigma 1 to sigma M. And then we get an approximation of X that is UM times SM VM transpose. And you can see actually, if you sum the number of parameters that you need for this is N times M plus M singular values plus M times D. So it's certainly linear in D, linear in N. Is it possible that this actually gives you the same results as PCA? What do you think? Is it possible that this is related? It gives you the same problem as PCA? Or it's some new technique? What do you think? Remember, in PCA up to now, right, you have to solve some eigenvalue problem of the sample covariance, okay? And consider just for the analysis purposes that, we have center our data, right? So the sample covariance it's 1/2 X transpose basically, okay? So do you think we get the same answers? What do you think? So let me go back to the previous slide. All right, so let's try to calculate the eigenvectors and eigenvalues of the matrix X transpose X. All right, so if you take X equal US V transpose and you form X transpose X, it comes that X transpose X times V equal V times D, where D is equal to S squared. So basically, what are the eigenvectors of X transpose X? Is V, okay? And the eigenvalues are defined by the S squared matrix, all right? S squared matrix that I call it here D. And similarly, if you form XX transpose the other way around, it comes out that the eigenvectors of XX transpose is really U, and again, the eigenvalues are equal to D. So can you see why the sample covariance basically is defined by solving an eigenvalue problem in principle here, right? You see that's basically the same problem, that if somehow you truncate the singular values from sigma 1 to sigma d to sigma 1 to sigma m is the same as basically truncating the same corresponding problem that we did when we discussed about doing an eigenexpansion of the sample covariance matrix. Okay, so if you see this, don't assume that there's anything new. It's basically the same thing as doing PCA. So if you want to program this, let's say in MATLAB, you can do one line command on getting this truncation, all right? And obviously the cost of computation is the same as computing the eigenvalue directly for the sample covariance, but here you do it in the context of the data metrics directly. So a few examples, all right? If you take this image that is in pixel form is 200 by 320, so the rank of this image is basically 200, and you do singular value decomposition or PCA, and you keep 2 components or 5 components or 20 in reconstructing the image. You can actually see with 2 components you don't see very much, with 5 you don't see very much, but with 20 components out of 200, all right, you immediately see this guy showing up there, okay? You can see up, I know it's, your brain basically when it sees a bozo, it recognizes a bozo, okay? And similarly, you can do these things with these different variations of the digit 3. So you can take 10,000 of these versions of 3, where they vary by translations in X and Y and rotation. Each of these images lives in a pixel form 28 by 28 in 784 dimensions. And you can form the sample covariance, right? Do the eigenvalue analysis or singular value decomposition, and then actually what you get is these are the principal components where you do the projections in order of decreasing eigenvalues. This is the mean reconstructed value that you can get, okay? And in all cases, of course, this looks like a nice tree. And I mentioned a good way to figure out on where you truncate the expansions and how many eigenvectors you keep, how many principal components you keep. A good way to do this is to plot the distortion criterion here, which is the sum of the eigenvalues that you don't use in the principal subspace. So effectively, when this is being reduced to a certain value that you consider acceptable, then you can say that's a good value for M to use. Okay, and here is for the same problem. the same program, basically trying to do reconstruction. Once you reduce, let's say, the space in a subspace of dimension 1, you can see this is the reconstruction you get of this digit 3. In subspace m equal to 10, you get something a little bit better. In 250, you basically get almost the same original image, but don't forget the actual dimensionality of the image is 784. You know, there's lots of things, lots of programs in the notes. You can actually put your own little image, and if you don't want people to recognize you on your website, you can distort yourself and only provide the first 3 components, projection, and let them figure out who's that person, okay? So if you want to waste time, there's lots of things you can do on these things. Okay, let me just, we have 4 minutes, okay? So let me just tell you something other that is a byproduct of doing principal component analysis, and it's actually something that you get for free, okay? And that has to do with what is called whitening. Anybody knows what is whitening of the data? Usually when you process data, right, you like, you know, data to have mean, let's say 0, variance equal to 1, but what is whitening? In this case, you know, let's say we have 2-dimensional data, x and y, all right? This is a standard data set, but what does it's whitening of the data? I mean, we don't, so one way everybody does, right, is take x and subtract the mean, divide by the standard deviation, so it has 0 mean unit variance, and you do the same thing with y, let's say, you know, but what is whitening when you have multivariate data here? You want to have unit what? Unit covariance. All right, so you want to have a unit covariance. And you can actually achieve this for free when you do PCA. So if you want, you know, the standard way is take your individual data, right, and subtract the mean, you know, divide by the standard deviation, right? So this is what's called standardized data. But what I want is actually to be able to use data that have a unit covariance. And how is that possible? It's possible if you, as a sort of a small step in your PCA algorithm. So imagine that you have data xn, all right, in d dimensions, and so you compute the sample mean, that is x bar, and you do your eigenvalue problem that you need to do PCA, and now you transform the data from xn to yn using this nice equation that you see there, where L is basically the diagonal of the eigenvalues, and use the orthogonal metrics where you do your projections. So it comes out that if you try to compute, obviously the mean of this is 0, all right? And if you try to compute the covariance basically of the y's, and you follow the algebra, it comes out that the covariance is equal to I. So effectively, you do get whitening of the data, and it is very strongly recommended, actually, when you do this type of model reduction, since it is coming for free as an early step in your algorithm to actually do this transformation, okay? It doesn't involve any cost because, you know, it's a multiplication here. This is a diagonal metric, so you don't have to invert anything, and this looks nice. So in this case, you see on the picture on the left, the data have been standardized. Basically, each of the data has a unit variance, but the covariance is not unit. And here, you use whitening of the data, all right? So you get something like that. So when you do PCA here versus PCA there, you get something completely different. And it's 1:45. I don't have time to discuss this. Maybe I will do this on Thursday. If you look at this oil flow data set, this is where this is actually demonstrated very nicely. And there is a computer program that you can sort of consult on the whitening of the data. So anyways, we will continue on Thursday on the probabilistic version of PCA. And I will spend maybe 20 minutes on independent component analysis, but the rest of the topics I will basically have you to work on your own, because we need to move on Friday to another topic.